Welcome everyone to the final presentation of Project DoRo, which is a shorthand version of Dorm Rover. It's a remote control rover robot that can be controlled through a website. This is the final project for class ECE 4180 Embedded Systems Design at Georgia Tech, and the team members are Yilun Chen, Yida Wang, Xi Li, and Zhenjie Chu. Here we present a 30,000 feet high-level overview of the project. You can see the architectural design of DoRo is extremely modular and expandable. We're separating different functionalities of the project into 3 different modules, front-end, back-end, and driver libraries. So if you want to add additional features on the DoRo, you can easily do that by looking at different modules separately. You can also see we're writing different modules in different languages to suit their best purposes. The front end is written in JavaScript. It uses a framework called React.js, and it creates a website for users to control the system from a web GUI. The backend is written in Python. It uses a web server framework called Flask and exposes very low-level APIs from our driver libraries to the front end. The driver libraries are written in C++. It basically bundles very low-level functionalities such as writing to I2C registers or PWM outputs. It bundles these functionalities into API calls. And it compiles these code into .so shared object files so that it can be used cross-language.
So the front end of our project is a web GUI that can be opened up on any device that's on the same network as the rover and has a web browser. It provides flexibility in terms of not having to install any specific app on whatever platform that the user is using. What it does is that it basically sends user command to the backend, allowing for further processing. For example, on the right are the direction control buttons, where they call the specific function on the left that sends the corresponding command to the backend. The whole front end is built on a JavaScript library called React. It's a very powerful library. The beauty of it is that it allows each component to manage their own state. For example, we have a live video feed section on our GUI, which requires constant refreshing and re-rendering. However, most of the other stuff on the GUI does not require that. So it allows just the video component to update itself without affecting any other components on the web. It provides some performance benefit in terms of running more complex GUIs on whatever device, and also it's more friendly on the bandwidth as well.
Here's a more detailed walkthrough of our backend. You can see our backend is divided into 3 sub-modules. There's the firmware wrapper, which sets up all the C++ libraries and make them ready to use by the rest of the backend service. There's the camera utilities, which talks directly to the Raspberry Pi camera. And there's the web server, which exposes all these APIs and serves the front-end interface to a specific IP address. On the bottom left of the screen, we can see an example of library setup and function wrapping. You can see we're loading the library called motioncontrol.so, and we're setting the argument type of a function in that library called setSpeed to be ctypes.cint. That just means integer type in language C. You can also see the declaration of a function called goStraight, which basically calls the goStraight function from the motion control library. On the right side of the screen, we can see an example of RESTful API exposure by our Flask framework. You can see we're exposing all of the motion control and servo control APIs to a RESTful API called /command. It accepts HTTP post requests, and it's gonna extract all the payload from that request if it comes in, and then extract the keys. And then based on the keys, call specific APIs.
Hi, this is Ida. I'm in charge of developing two sensors driver libraries on this project. One is the LiDAR time-of-flight sensor, and another one is IMU. The VL53L0X is a time-of-flight distance sensor. This sensor contains a very tiny invisible laser source and a matching sensor. The VL53L0X can detect the time of flight or how long the light has taken to bounce back to the sensor. Since it uses a very narrow light source, it is good for determining distance of only the surface directly in front of it. The LSM9DS1 is a 9-degree of freedom inertia measurement unit, which contains a 3-axis accelerometer, 3-axis gyroscope, and 3-axis magnetometer, as well as a temperature sensor on a single chip. These sensors can be used to determine a very precise orientation and provide useful sensor reading for our project. Both LiDAR and IMU sensor uses I2C interface. The specific wiring instructions are provided on our GitHub website. All the sensor readings are collected and uploaded to our server, so you can see them in our demo video on the bottom right corner of the web page.
The driver library also includes two other parts, which are motion control and servo. The motion control includes H-bridge and two motors, which are controlled by PWM and digital output signal. The H-bridge enables the motor to rotate clockwise and counterclockwise. Since we have two motors, so there are 4 combinations, and so that we're able to build 4 functions to let the chassis to move forward, backward, to left, and to right. The example of one of the functions is shown on the lower right corner, the figure 2, motion control example. The servo is connected to the camera, so by controlling servo, we're able to turn the camera to the direction we want it to face. And servo control is implemented by the PWM output. By changing the pulse width of the PWM output signal, the servo will be set to a certain location and stay there until the pulse width change.